the last speaker of the day, invited speaker, is Sindri. He was a PhD student in our department, so initially automatic control, and then network system engineering at KTH. And then afterward, he moved to the Harvard University for a postdoc, where he is now. He has done a lot of work on communication efficiency, distributed optimization, contractor algorithms, and then I guess this presentation is going to be about some of them as well. So,
okay, thank you for inviting me. So I'm very excited to present this work on distributed optimization with some communication constraints. During this talk, please feel free to interrupt me and discuss or ask any questions, or if there is something unclear, then feel free to ask for any small thing. So we have a lot of time for it. Okay, so what I'm going to present today is joint work with a couple of collaborators, including Lina Onali, who's my postdoc mentor in Harvard University, Wahid Sorak, who I know from when I was a PhD student. Then I was actually I spent 9 months in Harvard University as a visiting student. And then Wahid was my host, but since then he has moved to Duke University. And then some of this work is also something I did during my PhD studies with Carlo, I guess you know. And also some of the work I've done with Hussein, who is organizing this course. And also Gunnar, who is a PhD student in Harvard. And also Simindu, who was a postdoc in Harvard and is now in UCF, with the University of Central Florida, where he's an assistant professor. Okay, so in the last few decades, we've seen major revolutions in the areas of computing and networking. First, with the invention of the internet, which has then been amplified with various wireless technologies that has enabled us to stay connected anytime and anywhere. So we're now on the onset of a new technical revolution, but ubiquitous communication networks are bringing automatic decision capabilities into almost any object, and thus making these objects into intelligent systems. And these systems are often referred to as the Internet of Things or cyber-physical systems, depending a little bit on who you talk to. But essentially, these systems consist of massive amounts of nodes or objects, so millions or billions of nodes. And we want these nodes to coordinate, to collaborate to solve kind of complicated problems, complex problems, and kind of jointly optimize some kind of global objective functions by communicating and coordinating. Okay, so some examples of this are, for example, what you can see here is some kind of a traffic network where we will in the future have massive amounts of automatic cars and sensors in the streets that will coordinate the traffic and essentially kind of optimize the traffic, kind of our comfort in the, when traveling, travel time, safety, and so on. So another kind of very prominent example is, for example, smart grids, which will consist of all our home appliances, smart meters, and smart generators that will collaboratively optimize the grid's performance in terms of environment and economy and user satisfaction and so on. So, and these kind of networks are becoming big and starting to have huge impact. And Ericsson estimates that there will be around 30 billion devices connected to internet in the next few years, and that this kind of a new technology will create multi-trillion dollar economy per year in the next few years. Okay, so and also kind of maybe more related to this course is that when we have these massive amounts of nodes or objects, these objects will be able to collect massive amounts of data, and if you want to learn something from this data, or create this kind of take this raw data and create some kind of knowledge, then we need to process the data somehow. And this data is going to be huge, so we need to. And the reason this data is useful is because it's so huge that we cannot process it on one machine. We have to process it on many machines. So, and typically people will think of some kind of data centers like this, or some kind of distributed kind of servers that we need to coordinate to solve some kind of machine learning problems. But in reality, a lot of this data is going to come from a lot of different types of devices, and this is what we saw in the last talk with the federated learning, where kind of all these different devices are going to collect the data, and then if we want to learn from it, then we have to kind of preserve all the various constraints of kind of communication constraints of the different devices, the privacy constraints, and so on. So it's a very challenging task to kind of create some kind of knowledge out of all this kind of data that is so distributed and comes from so many different sources. Okay, so here we come to kind of the main problem that I'm interested in, the problem I've mostly been studying, which is to study type of distributed optimization problems like this, where we have multiple nodes, let's say n nodes, that want to solve some kind of distributed optimization problem, like we have here, where we want to optimize the objective function f with a function of different decision variables of different nodes. Here I is the decision of node I. And this objective function could, for example, be some kind of estimation, or where each node has kind of a different data that we want to learn from. Or this could be some kind of resource allocation problem in communication networks or in smart grids, where we need to distribute energy resources. And then we have some kind of coupling constraints that couples the kind of decisions of the different nodes. And in machine learning problems, this is typically some kind of consensus constraints. We need to kind of ensure that the estimator on the different nodes kind of we agree on the estimator on the different nodes. Okay, and then typically we could have some kind of uncertainty in our problem. Okay, so the main kind of my main interest is to study kind of distributed algorithms for these types of problems, where each node in the network takes some kind of performs some kind of a local algorithm, which is defined by some function AI, based on local information and local communication, so communication to neighbors. So, and I mean, these problems appear everywhere. You can think about your favorite network. You can think about kind of a network of computers and servers, or you can think about network of cell phones or smartphones that you coordinate some problems based on some data, or you can think about drones. But kind of main thing is that we have some kind of distributed algorithms to coordinate these networks. Okay, so the main research challenges I'm interested in is first of all, kind of how do we create this kind of some kind of local algorithm so we can achieve some kind of a desirable global system behavior by solving some kind of optimization problems. How can we ensure scalability of these algorithms? But what I'm mainly going to discuss today is how can we kind of limit the communication in these algorithms while still kind of maintaining the performance of the algorithms. Okay, so and there are many different types of communication limits in networks. So I mean, we want to have kind of reliable networks. We need to have kind of when we communicate, then we are sacrificing privacy and so on. But the main focus of this talk is going to be how we're going to limit the communication rate, or kind of limit the number of bits we need to communicate to solve optimization problems. Okay, so kind of the main questions we're going to study today is first of all, kind of what's the minimum communication needed to solve certain optimization problems. So this is what has been called in computer science communication complexity. So where we find kind of upper bounds and lower bounds, kind of so we can kind of show that we have kind of a optimal, in some sense, communication scheme. How do we design efficient algorithms, in communication sense, for these problems? And also, what's the trade-off between how much information we communicate per iteration, for example, and kind of algorithm performance we get. Okay, so and for this talk, I will split it into kind of three parts. So I will start by discussing kind of limited communication gradient methods, where we do some kind of gradient algorithm like we have here, but with a small twist, where we instead of taking kind of where this P is our decision variable, where we want to do, and we want to take kind of a gradient step from this decision variable. But instead of taking kind of the true gradient, we take some kind of a quantized version of the gradient direction. Okay, so we start by studying this problem and find kind of a study kind of a minimum size of the quantization and study some limited communication algorithm in this sense. Then in the second part of the talk, I will discuss a little bit more specific problem where we can actually get much stronger results. So, and where we consider kind of quantization schemes that kind of depend on time, change by time. And here we will actually be able to find kind of a true communication complexity for these problems, kind of exact communication complexity in the sense that we can find tight upper and lower bounds for these problems. And then in the final part of this talk, I will discuss kind of this kind of general type of distributed algorithms. So if we consider just any type of distributed algorithms like we have here, where we have, let's say, n nodes. Each node, if you look at the kind of algorithm at node I, which is here, the node I will kind of update its decision by taking some algorithm step with a function of some information C, which is information that has been communicated from other nodes in the network, and X, which is the previous information of other nodes. And then we study kind of what happens, how we can maintain good properties of these algorithms when we quantize the communicated information. Okay, so let me start by presenting the first part. Okay, so here we consider this problem here, where we want to minimize some objective function D, and we have a decision variable P. So, and the notation here, I use here D and P because kind of a lot of the motivation for this work is when we do kind of a dual gradient methods, where we communicate a dual gradient. And I believe actually there was one of the student posters, a student presentation was about kind of dual decomposition algorithm, dual gradient methods. So kind of, and maybe you can take that a little bit as a motivation for this work. So, okay, so when we consider, again, this kind of a gradient algorithm, where we do a gradient step. But typically, when we do dual decomposition, then we typically need to communicate the gradient to perform the algorithm. And this is, for example, the case if we're doing a resource allocation. For example, if we are allocating resources in smart grid or communication networks, then typically we will consider the dual problem. And given a kind of dual variable or a price, we consider the price for each kind of resource in our network. Given a price, each of the different users will kind of make a local decision on how much of the resources they're going to use. So we need to kind of communicate new prices to the users, and we change the prices by doing a gradient step. So essentially we communicate the dual gradient to perform these algorithms. So this work we consider when we do these iterations, and we consider kind of this quantized version of the gradient method, where at each iteration we, instead of taking the true gradient, we quantize the gradient to some finite set of directions, gradient directions. Okay, so this is essentially just our problem. So, and the first question we wanted to study when we started to think about this question is, if we have this kind of set Q of finite, and here Q should be, here we're considering kind of finite directions. So we're approximating the gradient with some direction. So when is our set of quantized gradients, this finite set, when is this a good quantization? Okay, so it's kind of easy to answer this because we kind of know what we want. So we want, even though it might be difficult to kind of achieve what we want. So essentially what we want, we just want that our algorithm will work. It will solve, we want to create a set Q, so we can create an algorithm based on this Q, so we will solve these optimization problems. So for any well-behaved dual function D, we can find some directions in Q so we can solve this problem. Okay, so of course we cannot use this to check if our Q is good, but we will see that in a little bit, how to check if our set is good and how to kind of create such a good quantization set. Okay, so how do we determine, so kind of more specifically in this paper we studied kind of how do we determine if a quantization is proper or if it's good. And then also when we have some kind of a good structure, we can have some sufficient and necessary conditions for what's a good or proper quantization. Then we can actually start to study questions like what's the minimum size of such good quantization sets. So we will actually answer this question also in this paper. And then we're also interested in studying kind of when we are given such a Q, how do we decide what directions to use and how to choose a step size. And also another interesting question is that kind of what's the trade-off between having kind of very using many bits to communicate, so having kind of very fine quantization grid, and the performance of the algorithm. Okay, so to answer the first question, what's a good or proper quantization? So then if we have some set, let's say we have a set of finite directions, and let these red three directions be our finite quantization set, then we want to be able to somehow check if this is a good quantization set. And we can consider if we have some gradient. So what we show in the paper, and this could be a little bit intuitive, is that if we can cover the in this case the plane, so that for any gradient direction, we can find at least one direction in our quantization set that ensures that we are going kind of in a decent direction. So it essentially means that we can we are ensuring that we are decreasing if we go into this direction. Okay, and from optimization we know that for convex problems, if we for this half plane around with the normal, this is the gradient, all of these directions will be decent directions, but we need to ensure also. So if you look at the directions here, that it's properly decent. So we need to ensure that for any direction, any possible gradient direction, we need to ensure that there is some the angle between our gradient and the our closest point in the quantization set. The angle between them should be less than some theta, and this theta should be smaller than half a p. So it should be a proper cone. The difference here. Okay, so and we show in this paper that this is actually sufficient and necessary to ensure the convergence of the algorithm. So to show the sufficient condition, I guess you can imagine, we can ensure that if we have this property, then we can always find a decent direction and ensure our functions are always getting smaller and smaller, and getting properly smaller because our quantization direction is never going to be orthogonal or converge into something that is close to orthogonal to the gradient because we have this theta condition. But to show the necessary condition, we show that if there is some possible gradient that where we don't have a decent direction in our quantization set, then we can always create a problem which you cannot solve. So then I can always create a convex problem by using this this potential gradient, and I can create a problem which you cannot solve. So this shows that this is also a necessary condition to ensure that our quantization set can solve any convex problem or any smooth convex problem. Okay, so then we provide a couple of examples of such a okay.
So the problem that you can generate, the counterexample, is it probably a function of the initial point, right? Because if you change the initial point, then the previous problem that you designed would not work.
Exactly, yeah. You have to
So essentially, this is necessary condition for one specific, let's say this necessary condition if you want to make sure that this works for all the inputs. But then what if we just say that we randomly initialize the input several times?
Okay, so then with some probability you will not be able to solve it, and some probability you will be able to solve it. So for
but then how hard is this for, how hard is to come up with these examples? Why I'm saying that? Because okay, so essentially what you're saying is that there exists a class of problems, okay, or class of functions in the class of continuous functions, that if you start from that specific input, and if the function belongs to that subset of the class of functions, then you may not converge, okay? But then what is the size of this class of function compared to this class of continuous function? Because if it is very small or not dense essentially, then you can just somehow address that by just random initializations. So several times randomly initialize this algorithm and then you can converge, right? So I guess that in that case, this necessary condition gonna be you remain in just half space perhaps.
Yeah, so I mean, yeah, it's correct. For example, and it will depend. For example, if you have I mean, you can have a very bad. I guess in the worst case, you only have one direction,
Sure.
and then you will have to, then probably, if you start always kind of on the wrong side of the direction, then you will not converge.
Sure.
Yeah. So, yeah, this is it depends on the initial condition. That's correct. Yeah.
Yeah, I can imagine that this is about building a worst case example. Doesn't mean that worst case example happens or how frequently that can happen anyway. Okay, but that's good.
Okay, so one example is of a set of directions that will be have this property, proper quantization is, for example, if you just take the sign of the gradient. So, and this is typical, for example, if you're doing dual decomposition with many resources, then kind of each node, let's say one node takes care of one resource, then each kind of a node is communicating kind of a binary, just kind of the direction of the gradient. Okay, so, and then also we can find, also based on this definition, we can find actually another example which we can show that is a smallest size of proper quantization. This is just one example of smallest size of proper quantization, which if we just take kind of the basis vectors, here k is the dimension of the problem, and then we kind of take one node that kind of goes kind of in the opposite direction, kind of to the mode. Let's see. Okay, and this quantization will have k plus 1 points, where k is the dimension. So to perform this kind of a gradient algorithm, we will need log 2 of k plus 1 bits to communicate this kind of a quantized gradient. Okay, so, and we can also prove study a little bit kind of convergence rate of these types of algorithms. So for any so if you consider kind of for stopping condition, we consider kind of the size of the gradient. Then we can show that for any epsilon and any steps that we choose like this, then we get this upper bound on the number of iterations we need to do to achieve this upper bound. So, and what is maybe more nice if we choose kind of we can actually choose one particular, we can choose one particular step size which will give us kind of this upper bound. So we can see that kind of our gradient, the size of our gradient, kind of it will take, if you want to make it, it will grow kind of it will be upper bounded by the square of t, which is the number of iterations, and also something that is related to kind of how fine the quantization is. So, and this cos theta is kind of our theta from the definition. So we see kind of we get this kind of trait of that when we have a finer quantization, then this cos of theta will be closer to 1. So then we get kind of a faster convergence. But as kind of our quantization size our theta cover gets kind of more coarse with fewer bits, then this will be smaller, and then we will get kind of we will need more iterations to ensure convergence. Okay.
What is the process of the function?
It has to be Lipschitz. No, gradient has to be Lipschitz content. What is it? It's smooth, yeah. Okay. So, and then actually we figured out that for these kind of theta covers have actually been studied in the 60s, 70s in communication theory, where people are studying kind of Gaussian channels and trying to find kind of covers for unit spheres. So there actually exist many schemes to kind of create very efficient quantization schemes, which work well for our case. And these quantization schemes are usually based on some kind of randomization to cover the unit sphere. Okay, so there are some simulations. So we tested this algorithm on a test problem. And here you can see on the right side kind of the convergence of different algorithms as a function of a number of iterations. And here you can see that so the red line here and the black line are two different algorithms that use infinite bandwidth, or where we do no quantization. And then this black line is where we do kind of a normalized gradient, which is essentially the algorithm we are kind of quantizing, because in this algorithm we are not using yet the magnitude of the gradient. So and then we can see that by using only four bits per iteration, we are kind of getting the same convergence as we would communicate to no quantization. Okay, but of course there is a small gap between kind of using kind of the full when we do kind of use also the magnitude of the gradient, where we get this much faster convergence compared to using only the direction of the gradient. Okay, so we're a little bit now studying kind of how to bridge this gap here. Okay. So, and then this was all for, all of this work was for kind of an unconstrained case, where we had no constraint on the decision variable. So, but typically, for example, if we are doing dual decomposition, then yeah, in some cases we have no constraints on the dual variable. For example, if our primal problem has equality constraint, but if we have some inequality constraint in our primal problem, then we'll have some kind of a constraint here. So we're interested in studying if this generalizes to, if we, for example, do some kind of projected gradient method. So what do you think? Do you think it will work, or do you have any thoughts? That is also my feeling, but actually we can, for a very general case, we can actually provide a couple of counterexamples showing that it will not work. So for example, but in some good cases it will work, but in some cases it will not work. For example, here we are considering a constraint problem, and here the gray area is our constraint. Here these black kind of thick lines are our kind of quantization sets, quantization directions. So, and here you can see that if one of our quantization direction is orthogonal to our constraint, then we can get actually stuck in a non-optimal point. Because then so this is our gradient, so we should go in this direction, but we kind of project it to this direction, and then actually, because we are progressing to this point, we are kind of getting stuck in this fixed point, which is not the optimal solution.
So we can't be solved increasing by reducing theta? So
yeah, so I mean, then if you would use another, I mean, for this particular quantization, like given a quantization, I can create a constraint that is not good. Okay, and then we can also, in this case, we can what's happening here is that we are not actually going in the descent direction anymore, because kind of when we kind of project to the kind of quantization set, then we are actually, and project then again to the constraint, then we kind of are going to a non-descent direction. Okay, so in general this doesn't work, But when we do the sign of the gradient and are projecting to the positive orthant, which is actually what we want, and this is actually the case for when we do dual decomposition. Then we typically want to do this, project to the positive orthant, and then this works fine. Then we get all the same results as before. Okay, so and this is like a theta cover with where we have this, the cos of theta is 1 over square root of k, where k is a dimension. And here we communicate 1 bit per dimension. And then, I mean, this applies to many algorithms, dual decomposition algorithms. For example, if you do TCP flow control or any type of dual decomposition for network flow, or if we do distributed resource allocation in power networks. And then also we have now some recent work where we show how we can do kind of a voltage control in power systems based on kind of some feedback measurements, where we're actually using this scheme with a small modification to fit this control problem, and it works very well for this. Okay, so this is the first part of the talk, where we discussed the limited communication gradient method. So for the second part, we're going to consider a little bit more specific problems and get a little bit stronger results. Now, consider, so now I want to find kind of the tight upper and lower bounds for finding a communication complexity for solving these similar types of problems that we studied before by using a gradient type methods. And typically, and we will consider this problem here, where we want to minimize a function d, a dual function, subject to some p, which is in some finite interval. Okay, and we assume that d is L-smooth. Okay, and this is actually kind of the dual problem if we are solving a resource allocation problem, where we have one constraint but many users. Each utility function is strongly concave. And we have some kind of bound on the gradient at the end, kind of at the end point of this interval here. So, and okay, and then this kind of this bound will correspond to our interval here. So then we get this upper bound on our dual function. Okay, so this is our problem class of the study. So we get these dual problems, and for all the results here, I can translate into the primal problem results. So I can any bound here, any tight bound here, I can find the tight bound that corresponds to it for the primal problems. So we have these problems of dual problems, this class of dual problems, where we want to minimize function d with this constraint that we are p is in the interval from 0 to p, and d is convex and L smooth. Okay, so and here we consider here we want to consider any quantization schemes that any quantization of any quantized gradient method. So we are not limited to kind of predefined set of direction, but now we consider any direction is allowed in our quantization scheme. So and here, so the algorithm we have is something that we do kind of this type of gradient method, where kind of the quantization, this function theta t, which is a quantization at time t, is a function of all the previous gradients. And this is in this set here, qt, and this qt can change over time, and the size of qt can be as large as we want, or has to be finite, and corresponds to this kind of rate of how many bits we communicate per iteration. Okay, so this can be any quantization scheme. So, and the questions we're going to answer now is, first we want to find kind of the minimum number of bits in total for achieving epsilon accuracy, so finding an epsilon solution to this problem, and also something that we call B complexity, which is the optimal achievable accuracy, kind of the best accuracy we can achieve by using B bits. Okay, so here we consider this optimal criterion is that we, based on our particular quantization scheme, So this t is the number of iterations we need to find an epsilon accurate solution for a problem d and using quantization q. Okay? So then kind of our epsilon complexity, which should be kind of the number of bits we need to find an epsilon solution, will be, and we define this in a min-max sense. So we find the kind of we minimize over all quantization schemes, all possible quantization schemes, and for each quantization scheme we find the kind of the worst, or we kind of maximize find the worst problem, find the problem that takes the most number of bits to solve. Okay? So you follow this definition. So yeah, this is just for any quantization you give me, I will give you always a kind of the worst problem for that quantization scheme, and then and the number of bits you need to solve the problem, and then we minimize that over all the all possible quantizations.
Now, one thing quantization is stationary, or quantization is changing over time?
So it can be changing over time.
Can be changing over time, but then you don't have index.
So this one has index.
Yeah, you don't have that, but then you use epsilon complexity term this time.
So the reason, so it's kind of included in here. So here we have so here we have, so this is a set of quantization, and then of course we need some initial point, which will be part of the quantization, and then we just any functions will be also, this can be any function that
Okay, so Q have something like some hidden index T.
Yeah, exactly. Okay, so we start by finding the, okay, so in this paper we show that the first result shows that kind of we can actually find kind of the tight epsilon complexity for this problem. We show there's a log 2 of p related to p and divided by 2 epsilon. Okay, so to prove a lower bound for this, we actually show that when we have this interval from 0 to p, then we can find certain amounts of points in this interval. This would be when we have b bits, we have 2 of b points, which we can use to cover the interval. And then we can ensure that we need that, if we want to get epsilon accuracy, then we need that then we need at least p divided by 2 epsilon points. Okay? So we can show this for any quantization. So for any quantization you give me, I can always find kind of a point that is in epsilon distance away from that point, if I use fewer bits. And for the achievability, or for the kind of algorithm that achieves this, before I discuss the algorithm we used, so actually one thing that is kind of interesting is that we are getting actually, so you can see that even if we replace kind of the number of bits with, so if you kind of translate this to kind of a convergence rate in terms of bits, kind of a solution accuracy we get for using b bits, then we get kind of a linear convergence rate for this. And it's kind of interesting because even if problems with this structure, in general, we need kind of a 1 over t squared bits to solve it. That's kind of the optimal convergence rate. But we are kind of exploiting that we have kind of a one-dimensional problem here to solve this. So we can actually use just like a bisection to solve this problem. And we can actually use also a quantization scheme that will achieve bisection to achieve exactly this bond. Okay, and then we can also translate this to the primal problems. Okay, so this is the first part of the paper, but actually in real world applications where we're using some kind of feedback to solve a problem. For example, if we're considering this problem again, and this dual problem, then typically we have some control center that is communicating kind of the prices to different users that will take kind of a local decision. Okay, and either might need to communicate information back, or often we can do we can measure this, because this is just the difference between supply and demand, which can, for example, be measured usually in power systems by measuring the frequency in the network, or in the communication networks by kind of measuring packet drop or something like this. So essentially what we have is that we go from kind of the original problem, then we do this measurement, and then we communicate kind of the quantized information to the users that then take action, okay? So, and what can happen when we take some kind of action is that we might kind of violate the feasibility of the problem. So you can imagine if if we have this constraint in a problem, if the users are taking too much of the resources in the, for example, in a power system, then it will cause a blackout. So we need to kind of study kind of the communication complexity when we have, while also ensuring that we do not violate the primal feasibility of the problem. Okay? So then we're interested in studying kind of the communication complexity with this additional constraint on the problem. So, and to do that, we need to consider kind of the original problem class. So this is just our problems, where we have all possible primal problems in this form, where we have mu is the kind of a strong convexity constraint, or the utility function should be strongly convex. We have n nodes, and we have this p condition on the gradient of the utility function. So then we want to find, then we define something that we call primal feasible quantization, Q, which is a quantization that ensures for any problem in this class, our quantization should be able to ensure that we do not violate the primal feasibility constraint at any iteration while achieving convergence. Okay? So, and we define this new class of our quantization function, or quantizations, which is, we need to take as input kind of the mu, n, and p, because this will kind of define our kind of what class of primal problems we want to kind of ensure that we do not violate the constraints of, and then also we call this kind of a PF, or primal feasible quantization schemes. Okay, and now I'm interested in studying what is the epsilon complexity for these primal feasible quantization scheme. Okay, so we define it in a very similar manner as before. So we want to find for any quantization scheme, we want to accept here, we want it to be not any quantization scheme, but we want it to be any primal feasible quantization scheme. We want to find kind of the worst dual problem, which will then correspond to, where this L will correspond to the Lipschitz constant related to mu and n. So we have kind of a direct correspondence between these dual problems and these type of primal problems. And that will be kind of the number of bits we need to achieve that. Okay, and here, remember that we are, this t was something related to how many bits we need if we use, how many iterations we need to, if we use this quantization scheme, this dual function, and we want to achieve epsilon accuracy. Okay, so, and actually we started by realizing that actually this is not possible. So if we consider this measure of optimality, then actually the communication complexity is going to be infinity. So, and the reason is that essentially for any quantization scheme, I can always, and any number of bits, I can always find a problem that will take b bits to find the epsilon accuracy. So it means that when we solve this min-max problem, then I can always create so bad problem that you will need arbitrarily many bits to solve it to epsilon accuracy. Okay? So, and this is actually a little, this is also related to, for example, if you do a gradient method, and you have, then you can also do this, for example, just for typical gradient method, you can show that if you only have L smooth objective function, then you can actually show that finding kind of a point that is arbitrarily close to kind of the optimal solution, you can make it as bad as possible, arbitrarily bad. So that's why usually when we study this class of problems, we consider instead of considering kind of how close the solution is to the optimal solution, we actually study it in terms of objective function value. For example, when we have strongly convex functions, then we will study convergence in terms of objective or decision variables. But when we have, for example, objective function which is only convex and smooth, then usually we can only find bounds on the objective function value, which we do here. And if we consider this, then we can actually show that the communication complexity will be related to 1 over epsilon. And essentially what we show is that we create a quantization scheme which is kind of similar to very conservative gradient method, which ensures that we kind of never violate the bound. But we can also create a problem that for any quantization schemes where this is the best thing we can do. So
you want to overestimate.
Yeah, so I can always create a problem where you, for any quantization scheme, if you don't follow this if you're not this conservative, then I can always find a problem where you will overestimate.
Yeah, absolutely.
Yeah.
So the thing is, you're going to the reverse overestimation just to make sure that there is no problem instance.
Exactly.
Due to the reshiftment, the smoothness of the problem. But one thing, what happened in the previous slide if you go for epsilon delta optimality? So if you allow a violation of delta in front of visibility.
So I mean for this one.
Yes. So instead of assuming that, actually it could be even to the previous slide actually. So it's just a definition, I guess.
This one.
Here, yeah, exactly. So the problem class is that, but then such that this is smaller than C, let's say this is smaller than C plus some delta. If you want to go with delta as close as possible to 0, then it should be positive.
I think it will not matter because then you could instead change it to a problem in this class where you add, for example, then you can, instead of having the C here, you can have C plus delta. And then you have a problem in this class already.
No, then the complexity could be in terms of C and delta.
C and delta.
And then
okay.
it could be inverse of delta, so if delta goes to 0, then essentially there is no algorithm. It's with that.
Yeah. That could.
Probably it could be inversely proportional to delta. At this point, I have no idea how. It's like delta to the square how. But yeah, I'm not sure.
Yeah, it's. I didn't think about it, and it's. I mean, it sounds reasonable. So that you could get a little bit some better results.
The first example that you can end up at every point is that just treat it just for any quantization approach that you have. Just make it problem extent that summation will violate that summation smaller than C. But then for that specific problem, there is always a delta that can make sure that it's smaller than C, but not smaller than C plus delta. Well, larger than C, but not larger than C plus delta for some conservative delta kind of things.
Yeah, it's
Probably.
it could work, but I will have to think a little bit about it. We can discuss. Okay, so just some simulations. We consider this on application example in smart grids. So we can see here that we have considered kind of convergence in terms of communicating bits. And the blue line is where we use kind of the primal feasible quantization scheme. The red line is where we use this the optimal quantization scheme. And these two here are the upper bounds, kind of respectively for the when we have no constraints. This is the upper bound, and this is the upper bound when we have constraints. Okay, so this seems very good. So the red line is very close to the upper bound, but the blue line is not very close to the upper bound. And this is actually because I used kind of a very practical example here. But I can also create, I can kind of create some toy example where actually this blue line will be very close to the, and that will satisfy all the constraints. So this is actually what we do for the proof. But I didn't show it here. But anyway, we're still seeing that when we do the primal feasible scheme, then we're suffering something. We're suffering in terms of number of bits we need to get a good solution accuracy. But if you look at kind of the constraints, then we see that, for example, the red line is violating the constraints or way to converging, whereas the blue line is kind of a very smoothly converging to a solution without violating the constraints. Okay.
Have you thought about local geometry? Because I would imagine that, for example, if you consider the smoothness, we are saying that there is one L for the whole function entire domain, but we know that individual points, we can go with local L, of course, for local smoothness parameter. And then that is usually much smaller, especially if you're close to the optimal solution. It's much smaller than that really. That perhaps correspond to that upper bound or something like that. But then have you considered the things that you don't know that parameter anyway, a priori, but how is the performance with respect to those L's?
Okay, so usually, so I think this is my experience that I think this is very often the case that usually you get some kind of a linear convergence rate because close to solution you will have some kind of a local kind of strong convexity.
Exactly.
This is the case for most problems. Exactly. And this is what we're seeing here. We have some kind of a local strong convexity, even though there's not a global strong convexity. So when we get close to a solution, we kind of get linear convergence rate. So, and this is what made it tricky to create the kind of a worst case. Then I need to make sure that we have a very poor solution close to the optimal solution. So
exactly. It actually reminds me to the Newton method where there are two different parts of the convergence. The first part is like a linear part or a sublinear part, where you get close enough to the geometric part, and then after some points you get to the geometry part, where the decreases geometry. So essentially, if you are, so you need to have some iterations to be close enough to the solution, and then once you're close enough to the solution, then in that strong convexity part, then it's gonna converge extremely fast. So that worst example, of course, there are some class of problems there, but in reality, probably that wouldn't happen. That probably could happen when you're far from the optimal solution, but whenever you're close to the optimal solution, that would be interesting to see how close, depending on the geometry. But then when you're close, usually you have a strong convexity anyway. Actually, much more than that, so you have a strong convexity and a very smooth function.
yeah, unless you're very unlucky.
Sure. That's true.
Yeah, but yeah, I agree with you. It's, I mean, this is based on kind of the worst case. Okay, so this is the second part of the talk. So now we'll discuss the final part of this talk. Okay, so the final part of this talk, we'll discuss kind of a general type of distributed algorithms where we consider some kind of a iterative distributed algorithm like the one we have here, where we have, let's say, n nodes. Each node kind of does kind of a local computation, which is a function of some algorithm function A. It's a local to the node. Some information is communicated from other nodes, and this is C. And here we can assume that C is something that has been communicated from neighbors in the network. And then some kind of a decision variable from the node from the previous iteration. Okay? And then we also assume that we kind of pick out, or we have some kind of function that kind of decides what local information I'm going to communicate to my neighbor. This is function C. Okay? So now we are interested in studying kind of for very general type of algorithms like this. We're interested in studying what happens when we do quantization. For example, if we want to perform this algorithm in some real-world system, then we need to quantize these communicated variables. So we will get kind of a quantized version of the algorithm, which is this algorithm here, where we update x, based on the same algorithm function. It's a function of q. Instead of here q instead of the original c, where q is some kind of some information that has been quantized. Where q is some quantized version of the variable c that we communicate. Okay, so kind of the main result of this work that we'll show during this talk is that we will show how to use kind of a constant number of bits in the quantization while still kind of maintaining some kind of good convergence property of the original algorithm. So if the original algorithm has some nice properties like linear convergence rate, then we can show how we can use kind of a finite number of bits per iteration to kind of ensure that convergence rate. Okay, so just to quickly give a small application to show you that this algorithm model is very general and it covers many examples. But since this course was on machine learning, you can consider some examples. So for example, if we have a couple of, let's say, data sets, could be from different cell phones, and we want to minimize, and we have different kind of labels and features from these different data sets. And then we want to minimize, based on the kind of different data sets, we want to minimize some kind of a local loss functions. And these loss functions are here we have kind of loss of the different data points on each node I. And then we can have some kind of a regularization part, okay, which is split between the different nodes, okay. And then this loss function could be, for example, a support vector machine where we have this hinge loss, or it could be logistic regression, or if this is not binary, then this could be just like a typical regression problem. Okay, so and typical ways to solve this type of problem is where we have this data on different nodes, and we need to communicate kind of and each node kind of has some kind of a estimator, and based on this local data, the node needs to communicate kind of the local gradient to some master node that will then do kind of a coordinate gradient descent method to solve this type of problem. And our algorithm model will cover these types of algorithms. And also, when we're trying to solve this type of problem in kind of a completely distributed fashion where only neighbors talk to neighbors and use only kind of local information. So for example, where we have a network of a couple of nodes, each node will communicate to its neighbors this variable c. And then we do some kind of a consensus step. And then we do a local, solve a local optimization problem. And this is essentially, I mean, there are many ways to do this, but this is based on dual decomposition, and we can discuss the details maybe after the talk if you're interested. But this is one way to do this, and then there's also kind of distributed gradient methods and so on you can use to do this. And these types of algorithms will also have be on the kind of a be on the general, be part of a general kind of a algorithm model that we consider. Okay, so, and actually for, recently there have been many people studying these types of algorithms. And you can see, for example, in the newest NIPS, many people are studying, particularly, so this framework, where people are, for kind of limited communication gradient methods. And I believe there was even like one lecture in the course was on this topic. Okay, so where we perform this algorithm, we need to communicate, we quantize the communicate variable, communicate over some network by using a finite number of bits, and then we perform the algorithm step. Okay, so our contribution compared to what people have been doing is that we consider kind of maintaining the convergence rate without increasing the number of bits we need per iteration, and also we have considered kind of very general algorithm model. Okay, so essentially what we'll show is that if algorithm has good convergence properties, then our limited communication algorithm will have the same convergence properties. And we will do this by designing an adaptive quantization scheme. So essentially here we want to communicate some variable c. So to do that we need to quantize it to some finite number of points. Could be this grid here. But essentially for our work, the kind of form of the point doesn't matter. It's mainly just that we have some kind of a finite sized grid or finite sized some kind of finite number of points that we can project to, and then we project our kind of communicated variable to this grid, where we will use b bits. This bit will be we'll use b bits to represent this grid, and then we will always center the grid kind of at the previous quantized at the previous quantized value, and then we consider this kind of the size of the grid. Okay, so the main idea is that we want to kind of create kind of adaptive grid that will kind of adapt to the convergence rate of the original algorithm. So, for example, if we where kind of this Q will make sure that we'll kind of our grid will kind of follow the communicated information over time, and then because we have this kind of nice convergence properties, or if we have nice convergence properties of the original algorithm, then we want to use these properties of the algorithm kind of to make sure that this grid becomes smaller without increasing the number of bits. Okay, so you can imagine that if the algorithm is converging, then we can make this grid become smaller, because then Q, then kind of the Q between two different iterations should always become smaller over time. Okay, but this we don't know. I mean, this is, we know this for the original algorithm, but not for the quantized algorithm. So now we want to see kind of how to kind of quantize, how to make this kind of a size of the grid become smaller. So we kind of manage to capture this C at every iteration during the algorithm. Okay, so we have some kind of trade-off when we choose this R between accuracy, kind of how fine the grid is, and also kind of maintaining the convergence, because we always have to kind of capture the communicated information. Okay, so because our grid cannot be so small that we will not be able to include the communicated information. So we show that if our original algorithm converges at a Q linear rate, so, and Q linear rate would just mean that it's converging kind of this linear speed kind of in log space. So this is the notation, or this is the notation people usually use in the optimization and machine learning community. So, but other people might call this exponential convergence or geometric convergence or something different. Then, and if we ensure that kind of our kind of adaptation, or kind of how fast we are decreasing the size of the grid. Okay, I actually forgot. I was going to include also the precise definition, but essentially it's something like alpha is something that is very close to, is a little bit larger than theta, and when we have more and more number of bits, then we will ensure that we will kind of get the same convergence rate as the original algorithm. Okay, and then we can see that kind of as we will converge at a linear rate if we have sufficiently many bits, and then kind of this convergence rate will converge to a kind of in terms of constant, will converge to the same convergence rate as the original algorithm when we have more bits. So just to illustrate this, we can consider this here line to be the original algorithm. So, and if we have, let's say, 2 bits, then we will still ensure that we will converge at a linear rate, which we have here. We will have a linear upper point here, but it will be a little bit slower than the original algorithm. And then we can show that kind of very quickly we will converge. If we use 4 bits, then we also converge at a linear rate, but get a little bit closer to the convergence rate of the original algorithm. And then here for this is a small toy example. When we use 6 bits, then we are converting using b bits per iteration. We're converting at almost the same rate as the original algorithm where there is no quantization. Okay, so this is kind of a small illustration also by using a real-world example that we considered, where we have multiple cell phones so I think we have like 1,000 cell phones, and I'm trying to do some kind of a logistic regression for this problem. And for this problem, it's not as nice as for the original problem, but here we have still, if we use like 32 bits, we will converge at a linear rate, but if you increase it a little bit, then we get closer and closer to the kind of original convergence rate. Okay, so, and then by using these results, we will actually get some kind of a theoretical bounds on kind of how many bits we need in total to ensure an epsilon accuracy to our problem, to make sure that kind of this quantity will be smaller than epsilon. And we, by a little bit kind of reformulating kind of the terms, we will get this b epsilon b, which is just kind of how many bits we need to get, when we communicate b bits per iteration to get epsilon accuracy. So this is kind of, this b here is something like related to, you can think about it as a packet size, or kind of a size of the packets we communicate per iteration. So we can actually see that there's kind of a trade-off between sending too few bits per iteration, where we get kind of we need to total a lot of bits, because we need to do such a coarse approximation of the communicated information. And then we can see that this gets smaller and smaller until we reach some kind of optimal packet size, where we kind of get use the fewest number of bits in total to solve to get this epsilon accuracy. And then after that, it's kind of this. It will be, we are not gaining anything, and we're actually kind of using more bits in total to, if you use more bits per iteration. And here we have used epsilon, I think, equal to 10 in the power of -6 or something like this. So this is a theoretical bound, and then we also kind of found the by in the case of the smartphones, we kind of computed this, and we found that the theoretical bound and the numerical bound is very similar. Okay, so just a few, a little bit of discussion of kind of the assumptions, a little bit more detailed discussion of the assumptions we need. So we need kind of the original algorithm to be linear convergence, or have this kind of pseudo contraction. So this is the original algorithm, distributed algorithm. This is the communicated information, and this is. So we remember this was just the form of our algorithm, and we can kind of. And this covers, for example, the fully distributed algorithm, where we can split this function into kind of many components of different, each component corresponding to different nodes. And we need this algorithm to be converged linearly, or this function to be pseudo contraction, and then we need small smoothness conditions on the algorithm function in terms of C, and also on the kind of a communicated function in terms of X. And this covers, for example, and we can actually show that this framework will cover many different algorithms. It will cover, for example, distributed optimization, like we saw earlier. It will cover many algorithms when we're learning equilibria in games. For example, if we do best response and gradient play, under some assumptions, of course. We need some additional assumptions, but for many interesting game theory learning in games, this applies. This applies also to power control in wireless networks, and also to Carlos Fast-Lipschitz problem class, and also for dual decomposition if we have strongly convex dual function, and also this applies also to consensus, and also if we have some kind of if we're trying to stabilize some systems in control theory, we can apply this. I mean, these assumptions will cover this one. Okay, so this is kind of the end of my talk. So I discussed kind of these three different schemes. The first two were related to the kind of how to quantize the gradient. First, kind of where we we had kind of a high-dimensional gradients and quantize it to kind of quantize the direction, find kind of the minimum quantization for the direction, and then we consider this a little bit more specific problem where we could get very kind of a detailed and kind of exact communication complexity, and then also we consider this kind of distributed algorithms where we did some quantizations and kind of maintained the convergence. Okay, thank you.